Hello viewers, myself Professor T.N. Oza presenting to you a new video titled Development of Quantum Mechanics. As we are aware, quantum mechanics is considered a bit new subject and a bit complicated. But once we understand its basic foundations, we can easily grasp the subject. I will try to introduce this subject under the following heads just for ease of convenience. Agenda, introduction, why Heisenberg's uncertainty principle disregards Newtonian mechanics or microscopic particles. Next, how to evaluate the arbitrary constants of integration, for example C1 and C2. Classical mechanics versus quantum mechanics. And lastly, a few lines about Erwin Schrödinger, the celebrated physicist. Introduction. The behavior of microscopic bodies, for example, motion, obeys the classical Newtonian mechanics because for them the uncertainty principle is negligible. When it was applied to microscopic particles like atoms, molecules, electrons, etc., it was found to be unsatisfactory. The following points for the reasoning are looking into new mechanics. First, the black body radiation experiment done about 1885 had shown that as the temperature of the body is raised, wavelength peak shifts towards shorter range, not continuously but discretely. This phenomenon could not be explained on the basis of classical theory available at that time. In 1900, Max Planck put forth his revolutionary theory of quantization of radiation. According to this theory, radiation is made up of discrete energy packets called photons of specific energy depending on the frequency. If frequency of radiation is f in per second, or f prime is wave number in reciprocal centimeter, and c is speed of light, L is the wavelength. The energy per photon is given by HF, HCF prime, or Hc by L. Einstein put forth his mass energy equivalence formula E equal to mc square. And in 1905, he explained the photoelectric effect, which is why different metals have different values of threshold energy or emission of electron upon being irradiated. This was a big jump in bringing forth new physics. Niels Bohr in 1913 proposed the idea of discrete circular orbits of radius r, of motion of electrons of mass m and velocity u in an atom. His proposition that angular momentum m u r must be an integral multiple of h upon 2 pi, so hypothetical, help understand the atomic emission spectra of elements. Next point, a big leap forward was the de Broglie formulation. It is wavelength equal to h upon momentum, which means that the atomic and subatomic level particles, there is coherence between energy and particle nature. Further credence arose by the Heisenberg uncertainty principle, which substituted the concept of certainty by uncertainty. His formulation states that if we want to measure a pair of variables like position and momentum for moving particle of very, very small size, atomic size, there will always be an associated uncertainty. Inspired by de Broglie's formulation, the laws of quantum mechanics were formulated by German physicists Born, W. Heisenberg, and P. Jordan under the name matrix mechanics. Erwin Schrödinger in 1926 proposed his famous second order differential equation under the name quantum mechanics. P. A. M. Dirac in 1928 introduced relativistic quantum mechanics, whereas in Schrodinger's method, the electronic spin has to be imposed as a variable. In Dirac's method, it emerges naturally. However, chemists are more familiar with the Schrodinger quantum mechanics formulation, and that is very popular among chemists. Why Heisenberg's uncertainty principle disregards Newtonian mechanics or a microscopic particle? We'll discuss a bit about it. In classical mechanics, motion of a body of mass m in one direction, say x direction, is governed by Newton's second law of motion. Equal to mass into acceleration given as mass into second differential d2x by dt2. Now, if we want to locate the position x of the moving body at a time t, we need to integrate equation 1. Upon first integration, equation 1 yields dx by dt. Then second integration gives x. Each integration introduces an arbitrary integration constant c1 and c2 respectively. We thus have x as a function of t, c1 and c2, where f is some function. That is x equal to function t1, c1, c2, equation 2. Here I have shown how integration introduces the arbitrary constant c1 and c2. How to evaluate the arbitrary constants of integration c1 and c2? We presume that at certain time, say t0, body is at the position x0 and has speed u0. Then we can write x0 as a function of t0, c1 and c2, equation 3. Similarly, for the velocity, we can write u0 equal to f time t0, c1, c2, equation 4. In this equation, f prime is the derivative of f, that is df by dt. Thus, if we know the force f, initial position x0 and velocity u0 or linear momentum, we can use Newton's second law of motion to predict with certainty the position of the body at any future time. However, this is not true for microscopic particles. For microscopic systems, the state of the system is defined by the state function or wave function psi, or any other symbol can be used with respect to the Cartesian coordinates x, y, z and time variable t. For example, for a system of two particles, we write as follows: psi is a function of x1, y1, z1, x2, y2, z2, t. But the system contains n particles. The time dependence of state function psi is given by the following time dependent second order differential equation, the famous Schrodinger wave equation. Equation is written over here. Summation is taken from I equal to 1 to n. Equation is minus h square upon 8 pi square mi multiplied by d2 psi over dx2 plus d2 psi over dy2 plus d2 psi over dz2 plus potential term v as a function of xi, yi, zi, t I equal to ih upon 2 pi d psi by dt. In this equation, mi is the mass and vi is the potential energy of the ith particle. Classical mechanics versus quantum mechanics. The importance of equation 6 is that it contains the first derivative of the wave function psi with respect to time, that is d psi over dt. A single integration of this with respect to t yields psi and introduces only one arbitrary constant of integration. Thus, the integration of equation gives psi equal to t plus c, constant of integration. Evidently, if we know the value of psi at initial time, that is t equal to 0, that is initial value of psi, No, then the arbitrary constant can be evaluated. It means that we can specify the initial quantum mechanical state of the system, and hence any future state at time greater than t0 can be predicted. Thus, it appears that the time-dependent Schrodinger wave equation is analogous to the second law of Newton, which is a classical mechanical equation that allows prediction of future state of a system from the knowledge of initial state parameters. However, classical mechanical results involve certainty, whereas quantum mechanical treatment involves probability, not certainty. In summary, quantum mechanics allows us principle to predict everything around us within the limits set by the uncertainty principle.